Hello everyone. Today I will give a presentation of my project in the course Wireless Communication. Um, my research area is analysis of OFDM techniques and its simulation. I will split all my talkings today into these 5 parts. First is the introduction. What is OFDM? OFDM, known as orthogonal frequency division multiplexing, is one kind of multi-carrier transmission method to achieve higher data rate of bits. Its core idea is to transmit the bits through multiple subcarriers, thus improving the overall performance, even where all the conditions of subcarriers are not so good. This kind of parallel transmission is feasible by separating the total bandwidth into several orthogonal subcarriers. This kind of orthogonality ensures to avoid the interference between the subcarriers. Nowadays, with the growing demand for higher data rates in various applications, OFDM has become an attractive solution, especially for 4G cellular network. OFDM applications are so various and will be more and more in the future. Nowadays, watching videos, playing online games, virtual reality, and autonomous driving are the main applications that require high data rates, and OFDM can play a key role in improving high data rates. OFDM successfully improves the data rates by allowing the subcarriers to have overlap spectrums like it is in the picture. Now let's talk about the principles and models behind OFDM. As we can see from its name, OFDM the OFDM technique is important. It's important to maintain when every two subcarriers always remain the orthogonality between each other. We can learn from the orthogonality from mathematical formulas in here, and we usually integrated two sinusoids over a time period. During the OFDM, we also implement fast Fourier transform and inverse Fourier transform to converge from time domain to frequency domain, or the inverse. Here we will also determine the minimum spectral separation in OFDM. Here we set to the reciprocal of t. T is the time period. We set to this value for optimal performance of the OFDM to let more subcarriers densely spaced that can utilizes the spectrum efficiency. This picture is the block diagram of the OFDM system. We can split the whole OFDM process into multiple blocks here. The upper part of the picture is the transmitter side, and the lower part is the receiver side. In order to use OFDM, we must implement multiple subcarriers to transmit the data in parallel. So at first, we should, after doing some channel coding to correct some errors in advance, after the simple mapping block, we will implement serial to parallel conversion to let the data transmit by OFDM in parallel fashion. And after that, we will do the IFFT that will do the inverse Fourier transform to transform the spectrum to time domain. And later on, we implement parallel to serial data for the ease of transmission through the channel. And then we use guard and cyclic extension because in OFDM, inter-symbol interference and inter-carrier interference actually exist. So we use cyclic extension to send a percentage of the whole symbol in advance to avoid this kind of interference. Then we implement digital to analog converter, and then we transmit the whole signal through the channel. It's in the whole channel. In this simulation, we will use additive white Gaussian noise because it is simple and an ideal case to analyze and study. And here, after the receiver receives the transmitted signal, it will do the inverse operation like we discussed in the transmitter part. So many blocks here actually are the inverse operations of what we'll see in the transmitter side. Here, let's talk about the specific OF design. At first, we will like to choose some key parameters before the whole design. The number of subcarriers, actually, what we normally see is that the subcarriers is only determined from the channel bandwidth, but actually it can be also determined by the complexity of the whole system. Here it is a formula that is shown here. Also, the fundamental frequency is usually set to the reciprocal of the symbol duration capital T, which is 1 over T. And the cyclic preference percentage is normally used in OFDM to relieve ISI and ICI, as we mentioned before. And here the picture clearly shows that how the cyclic prefix works. And here when we implement the OFDM, we will decide the modulation type according to different circumstances. Two common modulation types are QAM or QPSK. QAM is actually known as we see, is the quadratic amplitude modulation, and the QPSK is the quadrature phase shift keying. Both two measures have its own good points and bad points. Also, when it talks about the channel coding, we usually detect and we usually implement a block. Usually we use the method like trellis-coded modulation to detect and correct bit errors in frequency-selective fading channels. And this method we also implemented in the MATLAB simulation. And as for the channel environment, we use additive white Gaussian noise known as AWGN. I have mentioned it before. Related work actually as the conventional OFDM has been widely used and deployed in the real world, nowadays new research of topics focuses on how to update and improve the conventional OFDM to the whole new level. There are two new types of OFDM nowadays that are quite hot topics. That is DWT OFDM and MIMO OFDM. Last, it comes to the simulation part in MATLAB. The picture on the right are the steps of the major operations in MATLAB to achieve the OFDM system in the simulation, and you can have an overview of that. The picture on the left actually is the final plot. Actually, it is the bit error rates with respect to signal to noise ratio, and we can see that with the signal to noise ratio increases, the bit error rate becomes lower. And the last part, I will give a brief let you give a brief look of my code. Actually, here I use the convolutional coding as my channel coding method, and a number of subcarriers I choose 64, and single frame size is 96 bits, and total number of frames I determine as 100, and the modulation type I use here is the 16 quant. And also I determined the number of pilots and cyclic extension, and you can see here. First, I will generate a random binary formats of data, that is 0 or 1, and do the channel coding. And then I will use my convolutional coding to encode the data, and also this convolutional encoding is combined with time in leaving. Then I convert my signal from binary to decimal. Then I use the communication toolbox some functions like 16 quant modulation to do the modulation. And here I do the pilot insertion and adding the cyclic extension. Oh, I'd like to mention that here I will do the inverse fast Fourier transform to switch to the time domain. And I iterate the signal noise ratio from 0 to 50. And after the receiver gets the signal, it will do the inverse operations like removing cyclic extension, pilot synchronization, demodulation, and converts the decimal back to binary, and also do the inverse operation of time interleaving and decoding the data that is previously coded by the channel coding method. And finally, I calculated the bit error rate with respect to SNR to form the plot. And I want to run this. It will get the results just as what I showed in the last slides. Thank you for your watching.